When a Soviet pilot squeezed the trigger of the MiG-27's belly-mounted 30mm rotary cannon, the aircraft did not just shudder. It actively began to disassemble itself. The recoil from the GSH-630 cannon generated roughly 6,000 kilograms of reverse force, enough to completely arrest the forward momentum of a light car in a fraction of a second. Squeezing that trigger unleashed an extreme kinetic shockwave that violently ripped through the aircraft's centerline. In the air, this mechanical violence snapped landing gear doors open, shattered landing lights, jammed the flight controls, and routinely knocked the primary navigation avionics completely offline. Sometimes the physical instrument panel would unbolt itself from the dashboard, falling into the pilot's lap. This was not a flawed experimental prototype flying on the bleeding edge of aerospace research, nor was it a desperate wartime improvisation. This was the Mikoyan MiG-27, the meticulously engineered backbone of Soviet tactical strike aviation during the late Cold War. To understand the MiG-27, you have to abandon Western concepts of close air support. In the West, tactical aviation evolved toward the precision scalpel. The aircraft loiters, communicates with ground controllers, identifies a specific target, and drops a guided munition with pinpoint accuracy. The Soviet Union, however, viewed the battlefield through a fundamentally different lens. To Soviet planners, tactical air power was simply flying artillery. It was an extension of the mechanized infantry and armored divisions rolling across the plains of Europe. The objective was not necessarily to hit a single tank with a laser-guided bomb, but to saturate a grid square with overwhelming unguided firepower at supersonic speeds. The MiG-27 was the physical embodiment of this doctrine. It was designed to fly at treetop level, moving at near supersonic speeds to evade radar and ground fire, deliver a devastating payload of rockets, cluster munitions, or cannon fire in a single high-speed pass, and immediately egress. There was no loitering. There was no lingering to assess the damage. It was a brute force instrument, a high-speed delivery vehicle for unguided chaos. But turning this doctrinal theory into a reliable, mass-produced machine required extreme engineering compromises. If you enjoy detailed deep dives into military engineering and the tactical doctrines that shape these machines, subscribe to the channel. I've got a lot more planned. The origin of the MiG-27 is a study in forced adaptation. The aircraft was not designed from a blank sheet of paper to be a ground attack platform. It was the bastardized offspring of the MiG-23, a high-altitude supersonic interceptor built to chase down bombers. Taking a high-altitude interceptor and forcing it to fly in the thick, turbulent air at ground level is an aerodynamic nightmare. The first thing the engineers at Mikoyan had to do was rip out the interceptor's primary sensory organ, the massive Sapphire-23 radar. A ground attack aircraft operating in the 1970s did not need a heavy air-to-air radar. Removing the radar dish and its associated cooling equipment drastically changed the weight distribution and the physical profile of the aircraft. In its place, engineers installed a sloping, armor-plated nose section. This earned the aircraft the nickname Utkanos, or the Platypus. This drastic physical alteration wasn't just for weight savings. The sloping duckbill nose fundamentally altered the pilot's forward visibility. In the original MiG-23, the pilot sat behind a massive radar cone, looking out through a heavily framed canopy that offered dismal downward visibility, a fatal flaw for an aircraft supposed to fly 50 feet off the ground and visually acquire targets. The platypus nose gave the MiG-27 pilot a 15-degree downward viewing angle. While still claustrophobic by the standards of an F-16 or an A-10, it was a massive improvement that allowed the pilot to actually see the ground they were meant to attack. Inside this new nose sat the PRNK-23 navigation and attack system, which included the CLEN-PM laser rangefinder. The system was designed to automate the attack process. The pilot would designate a target visually. The laser would bounce energy off the target to determine the exact slant range, and an analog computer would calculate the ballistic trajectory of unguided bombs or rockets, giving the pilot an automated release cue. In theory, this turned dumb bombs into highly accurate munitions. But this introduces the first nested loop of the MiG-27's engineering saga. You have a system designed to calculate precise ballistics at high speeds. But the PRNK-23 system was built with early Cold War Soviet electronics, heavy, complex analog computers that relied on physical gyroscopes, delicate wiring, and fragile vacuum tubes. To work accurately, these systems needed a stable platform. However, the MiG-27 was anything but stable. Flying at 900 kilometers per hour at an altitude of 100 meters means flying through heavily disturbed, turbulent air. The thermal drafts and mechanical turbulence near the surface battered the airframe. The analog targeting computers were subjected to constant, violent vibration even before weapons were fired. The precision the duckbill nose and the CLEN-PM laser were supposed to provide was consistently eroded by the physical realities of low-level flight. To solve the low-level stability problem, the engineers relied on the aircraft's defining physical feature, its variable geometry wings. Swing wings were the aerospace engineering obsession of the late 1960s and 1970s. The concept is straightforward. By sweeping the wings forward to a 16-degree angle, the aircraft generates massive lift, allowing it to take off from short, rough frontline airstrips, carrying a heavy payload of weapons and fuel. Once airborne, the pilot can sweep the wings back to 45 degrees for efficient cruising, or tuck them all the way back to a dart-like 72 degrees for high-speed, low-altitude attack runs. When the wings were fully swept back, the MiG-27 had an exceptionally high wing loading. Wing loading is the total weight of the aircraft divided by the area of its wings. A high wing loading means the aircraft is less susceptible to sudden gusts of wind. It cuts through the low-level turbulence like a heavy dart, providing a remarkably smooth, stable ride for the pilot and the targeting computers. For a brief moment in the attack run, the swing wings perfectly solved the stability issue, giving the analog systems the smooth platform they desperately needed. But the price paid for this aerodynamic solution was severe. Variable geometry wings are an engineering penalty box. The massive titanium wing pivot box located in the center of the fuselage is incredibly heavy, eating into the aircraft's payload capacity. More importantly, when wings move, you cannot easily hang things on them. You cannot attach fuel tanks or heavy weapon pylons to the outer sections of a wing that needs to swing backward into the fuselage. Because the sweeping wings severely limited the amount of external hardpoints available for weapons, the aircraft could not carry the sheer volume of external cluster bombs and rocket pods required to saturate a target area purely with underwing stores. The MiG-27 had pylons under the fixed wing gloves and under the fuselage, but it simply lacked the expansive wing real estate of a fixed-wing attacker. The engineers faced a strict weight and space limitation. They needed to provide this aircraft with overwhelming concentrated firepower to fulfill the flying artillery doctrine, but they were running out of places to bolt weapons. Their solution was to turn to internal firepower. If they couldn't carry enough external bombs, they would give the aircraft a gun capable of destroying armor, concrete, and vehicle columns in a single high-speed pass. This brings us to the GSH-630. To understand the sheer insanity of this weapon, it is necessary to compare it to the American GAU-8 Avenger, the massive rotary cannon that defines the A-10 Warthog. The A-10 was literally built around the GAU-8. The aircraft is a subsonic, heavily armored weapons carriage designed specifically to absorb the immense recoil of the 30mm cannon. The nose gear is offset to allow the firing barrel of the gun to sit perfectly on the aircraft's center line, ensuring the recoil pushes straight back without throwing the plane off course. The Soviet engineers did not have the luxury of building the MiG-27 around its gun. They took a supersonic interceptor airframe and essentially bolted a massive 6-barrel 30mm rotary cannon to the belly. But the physical mechanics of the GSH-630 were fundamentally different from the American gun, and these differences created the aircraft's most infamous operational hazards. The American GAU-8 relies on a hydraulic or electric motor to spin the barrels. This means it takes a fraction of a second for the barrels to reach their maximum rotational speed. The Soviet GSH-630, however, was a gas-operated weapon. It used the explosive gas from the fired cartridges to violently blow back the mechanism and spin the barrels. This meant the gun did not require a heavy external electric motor, saving precious weight. More importantly, it meant the gun achieved its maximum rate of fire instantaneously. The moment the pilot pulled the trigger, the gun was spitting out 6,000 rounds per minute. The instantaneous application of that much kinetic energy was catastrophic to the carrier aircraft. The GSH-630 fired a 30 by 165 mm projectile. When firing at full speed, the gun produced a vibration frequency and a recoil shock wave that the MiG-27 airframe simply could not diffuse. The aircraft was a modified interceptor, built for aerodynamic speed, not for absorbing the impact of a heavy artillery piece bolted to its undercarriage. Let's shift from the theoretical engineering to the raw, jarring reality of the cockpit. When a pilot lined up a target, perhaps an armored column or a fortified structure, they would push the nose down, accelerate to near supersonic speeds, and squeeze the trigger. The immediate result was an auditory and physical assault. The airframe would violently shudder. The gas expelled from the muzzle was so voluminous that it would occasionally get sucked into the aircraft's engine intakes, starving the Tumansky R-29 jet engine of oxygen and risking a complete compressor stall at low altitude. But the structural damage was the true hazard. The vibration tore through the fuselage. It was a common occurrence for the landing gear doors, secured by heavy mechanical locks, to simply shear open under the stress, instantly inducing massive aerodynamic drag. Landing lights mounted on the undercarriage shattered as a matter of routine. The VHF radios, relying on fragile internal connections, would frequently fail, cutting the pilot off from ground control. Most critically, the violent shaking would completely scramble the PRNK-23 targeting computer and the CLEN PM laser. The very system designed to give the pilot a precise aiming point would fail at the exact moment the weapon was fired. The analog gyroscopes would tumble, the dials would spin uselessly, and in several documented instances, the screws holding the main instrument panel in place sheared off entirely. The engineers attempted to mitigate this. They reinforced the belly plating, added stronger shock absorbers to the gun mount, and restricted pilots from firing long bursts. A standard burst was restricted to just a fraction of a second, dispensing around 30 to 40 rounds. Even with these restrictions, the aircraft was fundamentally at war with its own primary weapon. The flying artillery doctrine had pushed the airframe beyond its structural limits. The propulsion system of the MiG-27 further illustrates the brutal compromises required by its operational profile. The original MiG-23 interceptor used a complex engine with variable intake ramps. These ramps would move automatically at different speeds to slow down the incoming air, ensuring the engine could operate efficiently at Mach 2. But the MiG-27 was never going to fly at Mach 2. It was designed to fly low and fast, but safely in the transonic region, around Mach 0.9 to Mach 1.1. Therefore, the complex, heavy variable intake ramps were entirely stripped out. The MiG-27 featured simplified fixed-air intakes. This saved significant weight and reduced maintenance complexity, but it completely capped the aircraft's top speed. Behind those fixed intakes sat the Tumansky R-29 B300 turbojet. This engine was a brute. It was optimized for low-altitude operation, specifically tuned to provide massive, raw thrust in dense air. The exhaust nozzle was also simplified. On an interceptor, a highly complex variable exhaust nozzle expands and contracts to maximize thrust at high altitudes and supersonic speeds. The MiG-27's engine featured a much simpler two-position nozzle. It was either open for afterburner or closed for standard military power. This engine provided extraordinary low-level acceleration. If a MiG-27 pilot encountered enemy air defenses, they had the thrust to simply power through, accelerating away from the threat rather than trying to outturn it. But the Tumansky turbojet was notoriously thirsty and ran incredibly hot. It consumed fuel at a staggering rate, meaning the MiG-27 had a relatively short operational radius. It was a sprinter, not a marathon runner. It would launch from a forward base, sprint to the target, unleash its weapons, and sprint back before the fuel gauges dropped to critical levels. So, after seeing how it actually performed, dealing with extreme vibration, thirsty engines, and fragile analog computers, do you think the design approach was worth it? Let me know in the comments. The true test of any combat aircraft is not found on a test range, but in the dirt, heat, and chaos of operational deployment. For the MiG-27, that crucible was the Soviet war in Afghanistan during the 1980s. Afghanistan was an environment entirely unsuited to the MiG-27's original design philosophy. The aircraft was built to fly low over the flat plains of Germany, hunting NATO tank columns. In Afghanistan, it was deployed into high-altitude mountain valleys against decentralized guerrilla fighters. The high elevation and extreme summer heat of bases, like Shindand and Bagram, wreaked havoc on the aircraft's performance. Jet engines require dense air to produce thrust. In the thin, hot mountain air, the powerful Tumansky engine suddenly felt asthmatic. The aircraft struggled to take off with a full weapons load, forcing ground crews to drastically reduce the amount of fuel or munitions carried on each sortie. Furthermore, the tactics had to shift. The flying artillery doctrine of a single, massive, high-speed pass was ineffective against targets hidden in complex mountain cave systems or narrow ravines. The pilots had to dive steeply into valleys, exposing themselves to intense ground fire from heavy machine guns and portable anti-aircraft missiles. The primitive nature of the avionics became glaringly obvious. The Klen PM laser rangefinder was difficult to keep on target while maneuvering violently to avoid ground fire. Pilots often abandoned the automated targeting systems entirely, relying on the manual iron sight, their own judgment, and sheer volume of fire to suppress the target area. Because of the severe issues with the internal 30mm cannon, ground crews frequently loaded the aircraft with underwing unguided rocket pods, primarily the 80mm S-8 rockets. These rockets became the weapon of choice. A pilot could ripple-fire dozens of S-8 rockets into a suspected enemy position, blanketing a wide area with high explosives. It lacked the precision of a laser-guided bomb, but it fulfilled the brute force requirement of suppressing ground fire and denying the enemy the use of the terrain. However, the physical toll on the airframes was immense. The fine alkaline dust of the Afghan environment acted like sandpaper on the complex mechanical linkages of the variable geometry wings. The engine compressor blades suffered severe erosion from ingesting dust and debris during operations from austere airstrips. Maintenance crews worked exhaustively to keep the complex hydraulic and pneumatic systems functioning in an environment that actively tried to destroy them. The MiG-27 proved to be rugged enough to survive, but it required a massive logistical tail to maintain its combat readiness. While the Soviet Union eventually withdrew from Afghanistan, the operational life of the MiG-27 was far from over. As the Cold War ended and the Soviet Union collapsed, the massive fleets of tactical aviation were suddenly without a mission. The Russian Air Force, facing severe economic collapse, aggressively retired its single-engine tactical fleet. The complex maintenance requirements of the swing-wing mechanism and the thirsty Tumansky engines made the MiG-27 an easy target for budget cuts. By the mid-1990s, the vast majority of Russian MiG-27s were rusting in storage yards. But the aircraft found a second, highly active life in South Asia. The Indian Air Force had purchased the MiG-27, locally producing it under license and naming it the Bahadur, meaning valiant. The Indians understood the inherent flaws in the Soviet avionics and embarked on an ambitious program to modernize the airframe. The Indian upgrade program serves as a fascinating case study in mating brute force Soviet hardware with advanced Western electronics. The Indian Air Force essentially hollowed out the analog brain of the MiG-27 and replaced it with modern mission computers, new heads-up displays, and advanced navigation systems, drawing from Israeli and French technology. This modernization attempted to solve the original conflict of the airframe. By installing reliable, solid-state electronics, the Indian engineers gave the platform the precision it had always lacked. The pilot workload was drastically reduced. They no longer had to fight with tumbling analog gyroscopes or uncooperative mechanical dials. The upgraded Bahadur saw extensive combat during the 1999 Kargil War against Pakistan. Once again, the aircraft was thrust into an extreme, high-altitude mountain environment. Operating at elevations that pushed the limits of aerodynamic performance, the MiG-27s were tasked with striking fortified bunkers built into the peaks of the Himalayas. In this environment, the raw thrust of the engine and the high wing loading of the swept wings allowed the aircraft to conduct strikes in conditions where lighter, less powerful aircraft would have struggled. However, the modernization could not fix the fundamental aerodynamic limitations of the airframe. During the Kargil conflict, an Indian MiG-27 suffered an engine failure, likely a compressor stall induced by ingesting exhaust gases from its own weapons or extreme maneuvering at high altitude, resulting in the loss of the aircraft. the Indian Air Force continued to operate the modernized MiG-27s well into the 21st century, relying on them as dedicated strike platforms. But the inevitable march of time and the physical fatigue on the airframes could not be ignored. The maintenance man-hours required to keep the variable geometry wing pivot mechanism safe for flight grew exponentially. The airframes were physically exhausted, battered by decades of low-level flying, structural vibration, and harsh operational environments. In December 2019, the Indian Air Force finally retired its last squadron of MiG-27s, bringing the operational history of the Platypus to a close. Looking back at the entire life cycle of the MiG-27, it serves as a monument to a highly specific, now obsolete philosophy of warfare. The central conflict of its existence, trying to force an interceptor airframe to act as low-altitude flying artillery, was never truly resolved. It was merely managed. The engineers at Mikoyan successfully built a machine that could deliver terrifying amounts of firepower at blistering speeds. They created an aircraft that could survive the extreme turbulence of low-altitude flight and operate from austere frontline bases. But the compromises required to achieve this were severe. The violent recoil of the GSH-630 cannon, the heavy penalty of the swing wings, the thirst of the engine, and the fragility of the analog avionics all conspired to make the MiG-27 a highly specialized, deeply flawed instrument. It was an aircraft that required its pilots to accept a high degree of physical and mechanical risk just to operate its weapons. It was a machine that demanded exhaustive, grueling maintenance to remain in the air. In the end, the concept of the supersonic, unguided flying artillery piece was rendered obsolete, not just by the end of the Cold War, but by the relentless advancement of precision-guided munitions. Today, a modern multi-role fighter can deliver a smart bomb from 20,000 feet with greater accuracy and lethality than a MiG-27 could achieve by flying at 100 feet and physically tearing itself apart with cannon fire. The MiG-27 remains a fascinating artifact of aerospace engineering. It represents a time when brute force and raw mechanical power were viewed as the primary solutions to tactical problems. It was loud, violent, heavy, and unapologetically built for a massive mechanized conflict that thankfully never occurred. If you like this deep dive, leaving a like helps get it out to other military history fans. Thanks for being here.